Okay, hello everyone. In this video, we are going to understand what is RAG, which stands for Retrieval Augmented Generation. So let's understand why RAG is needed. Why is it that we should study about it? So we know that all these modern LLMs like GPT, Claude, Gemini, they're trained on huge amounts of data, right? And hence they are very powerful, very knowledgeable. However, they have one major limitation, which is they only know what they were trained on, which makes sense, right? For example, let's say a model, an LLM, was trained in September 2025 and some event happened in October 2025, right? Now, since the model was trained before that event happened, the model won't know anything about that event. However, if you ask it a question on that event which happened in September 2025, it will make up some answer, right? Because at the end of the day, it's just predicting next word, right? So it will make up a fact, which precisely is called hallucination, right? So that's a problem. So we can't use the LLM as it is if we want it to predict something on a recent event, right? So what are the solutions to it? Let's talk about that. One solution is retraining or fine tuning, which means given the new data that we have, let's keep retraining or fine tuning the LLM again and again, which again doesn't make sense, right? Because it's very expensive. You need a lot of GPU. Each update would require a new training, right? Which means if something happens or something changes, you would need to retrain, and that is very expensive. So doesn't seem like a very good option, right? The other option is prompt stuffing, which means whatever new information has come in, you pass that information in along with your query in the form of the prompt, right? Which means prompt stuffing. You stuff in that information in the prompt, and hence LLM should be able to answer any query based on that extra information that you have stuffed in. However, there is a limit to how long a prompt can you pass in, right? There is a context length for every LLM, and these days the context length is quite high, but even then you can't stuff in a lot of information. So this option is also not a good solution, right? So that is where RAG comes in. That is where we can make use of RAG. This is a situation where RAG would be helpful. It solves both these problems. It keeps the model lightweight and it allows the access to the recent information. How that happens, let's understand. So, as the name indicates, retrieval augmented generation. So, there are two main steps in RAG. First is retrieval and second is generation. In a traditional LLM, the only step is generation, which happens based on the model's existing knowledge, which is there in the form of parameters. In RAG, there's one more step that is added, which is retrieval, right? Which means before the generation happens, the LLM would be able to retrieve some form of knowledge from some source. We'll talk about the source and its form later, but for now, just know that there'll be some place from which the LLM can access some information, and that information can be used during the generation process, right? That's pretty much the big picture. You can take this analogy that traditional LLM without RAG is kind of a closed book exam, wherein the student cannot access any outside resource. The student has to answer only based on what they know, right? On the other hand, open book exam, the student can access external resources. The same is happening here in RAG. before the RAG is generating something, which means producing an answer for any question that you ask, it is allowed to access some extra knowledge in some format. So RAG is like an open book exam, if you take this analogy. Okay. Before we get into the details, let's take a look at the scenarios where RAG would be useful, right? So one scenario where RAG would be useful is when something keeps changing. For example, a company's policies. If the policies change frequently, you can't afford to retrain the model again and again. So that's a scenario where you would want to use RAG. The other scenario is a kind of information which is not available online generally. For example, some confidential information, you can say, or something that is not easily available online. For example, some medical details or some legal documents which are there with medical practitioners or legal practitioners, right? They wouldn't make every information accessible online. So of course, your LLM wouldn't have seen that. So for that scenario also, RAG is a good solution where we can pass in those documents which contain the extra information and can use in RAG before LLM can generate, LLM can access that information. Okay. Let's understand the workflow of RAG. So the user asks a query. Before that query is passed to an LLM, a vector database will be accessed, which would be containing some extra information, right? From this vector database, some relevant documents will be retrieved. This vector database would be containing a lot of documents, but only some of them will be relevant for the user's query. So those documents which are relevant for the user's query will be retrieved. These documents will then kind of be added to the user's query to form the final prompt, right? Which will be fed to the LLM. Okay. So in a default scenario without RAG, this user query will be passed to the LLM. But now there are some 3 steps that have come in. One is accessing the vector database and then retrieving the relevant documents and then kind of appending it to the user's query to make the final prompt. This is something new here. And after that, as usual, the LLM has got some information. It has got some prompt, and based on that prompt, it will produce the output which will be given back to the user. So this is broadly the workflow of RAG. Okay, now let's understand the main steps that are involved, like from an implementation perspective. Of course, the first step is to prepare the data for retrieval, right? We talked about vector database, and this database will be containing the data, and we need to prepare the data in such a form that it is easy to retrieve, right? So this is the first step. We have to prepare our data. Now the challenge lies in the fact that the data that we might have from medical or legal domain or whatever policies that we have, they might not be in a nice format, let's say question answer format, right? That might not be in a very nice format. Secondly, it might be in a different kind of files, for example, PDF files, reports, emails, text files, etc. Right? So we need to use several tools which can convert this data, which is in different formats, into one common form, into one common format, right? So that is what this load step will entail. Okay. Well, not only these files, we can also access information from some URL available online. That information can also be passed over here. So there's quite a flexibility in terms of what kind of data can be passed to RAG. Why? Because we'll convert into a common format. We'll see that later. Okay, once the data is loaded, the next step is to split the data into smaller chunks, right? Why do we need to do that? Because let's say there's a 20-page PDF and we try to keep it like this only, right? And then when retrieval happens, we would be retrieving this 20-page document. That will be too much information. Once again, the problem of keeping the limited size of prompt, that's one problem. Second problem is this PDF would have a lot of information, much more than what we need to answer the user's query, right? So we need a small piece of information, but for that we are just retrieving the entire document. That doesn't make sense. So what we do is we split each given document into small pieces or small chunks. Okay. So that's the second step. Now, the third step is after we have split the documents into smaller pieces, what we need to do is we need to convert each chunk into a form so that it is easy to retrieve, right? Now, that is where embeddings come into picture. We will see embeddings in a bit more detail later. For now, just know that each chunk will be converted into a vector containing numerical value so that it becomes easy to access each chunk. Okay, the next step is to store these vectors, which we will get from this embedding step. So we will store all these embeddings into what we call a vector store. Vector stores are used because they help us in easy retrieval, because we need to access the information in the runtime, which means the moment user accesses the query, we need to retrieve the right chunks from the database very quickly. So therefore we need something which is very fast. So we use what is called a vector database, and there are several options of vector database. For example, there's a FIRES, there's Chroma DB, there is Pinecone. Maybe we'll talk about that a bit later. So these are the four main steps if you talk about the implementation of RAG. Now let's talk about a bit of the parameters. So we talked about splitting the documents into chunks. What should be the right size of this chunk? Let's talk about that. So there are a couple of parameters that we will be seeing in the implementation also. So there's something called chunk size. Okay. What should be the right chunk size? Should it be small? Should it be big? Right? Now that is something that depends on the use case. Right? So there can be two extremes, that you use very big chunks. The other extreme is you use small chunks. If you use big chunks, you can think that it'll take a lot of time. In the I/O itself will take a lot of time. The response will be slow because, like I told earlier, it'll be a huge information in one chunk itself, much more than what is needed for the query. So in order to find the right information out of that big chunk will also take time, right? And if the chunks are very small, then in order to answer one user query, you would need a lot of chunks, many chunks you would need, and retrieving them also will take a lot of time, right? So that will lead to higher costs. So the right chunk size is somewhere in the middle. Again, what exactly is the right chunk size depends on the use case, right? So let's say you have a document which contains some recipes fruit recipes, right? So let's say the first recipe is about, let's say, apple pie, right? Second recipe is about, let's say, orange juice. And the third recipe is, let's say, what can be, banana bread, let's say, right? So one document contains these three logical pieces of information, right? Now, if you, one extreme is you keep all of them in one chunk, right? So let's say some user asks for apple pie, then this entire document will be retrieved, and here we are interested in this thing and not this thing, right? So that will be an extra irrelevant information, irrelevant context coming into the prompt. That's a problem. On the other hand, on the other extreme, let's say you have very small chunk size, let's say, I don't know, 50 characters. So then what will happen is your one recipe might require multiple chunks. So whatever information user asks for is scattered around in multiple chunks. So that will be another problem, right? So there has to be a good, an optimal size of the chunks, which depends on the use case. So generally we have 500 to 2000 characters in a real scenario. On an average, you might want to start with 1000 characters in one chunk. Of course, you can change it, but generally we start off with these numbers. 1000 characters per chunk is a decent size in a real world scenario. Okay. The other thing to look at is chunk overlap. So our chunks are not like this. So let's say this is a sentence, there's a piece of text, and this is your first chunk, and then, let me use another color. This is your second chunk, right? So there's a very, this is a boundary, and there's some amount of information that we want to keep, which is called chunk overlap, which means there's some information which we will keep in this chunk as well as in this chunk. Let's say this piece of information we would keep in chunk 1 as well as chunk 2. Why do we do that? Because you don't want to lose the context or the information which is present in the boundary, right? If you are making a sharp division over here, then whatever information is present over here in the boundary, half of it goes here, some part of it goes here, and some part goes here. So you might actually lose that information. So in order to avoid that, what you do is some part of information, in particular a few characters, you'll keep both in chunk 1 as well as chunk 2. That's called chunk overlap. So for example, in here, well, this requires some correction. Is the capital of France, and this will be first chunk, and of France, and is. So this part is present here as well as over here. So this is the overlap part. Okay, this is the overlap. So this overlap, you see, kind of acts like a glue between two chunks, right? And generally, what we do is 10 to 20% of the information we keep in the chunk overlap. Okay. Now, that you can see that some extra, extra number of chunks will be created if you're keeping some information in the overlap region, but that is worth it because that helps us not lose any useful piece of information. So the extra number of chunks that we end up creating is not a problem because that actually helps us retain some good pieces of information. Okay, so it's an important parameter to decide the value of. Finally, once the chunks have been created, like I said, the next step is to create the embeddings of these chunks, right? Why do we need embeddings? Let's understand. Some of you might have already an idea about embeddings, but let me quickly cover this up. So what embedding model will do is the following. It will take some piece of one chunk, it will take in this particular case, and it will convert it into a vector containing some numbers. The size of the vector will be pre-decided. So each chunk will be converted into a fixed sized vector containing numerical values. Right. Why is it that we need this? Let's also understand that. Why can't we simply do a keyword search? Right, that's one option. The user asks some query, and then there might be some keywords in the query, and then we can do a keyword lookup in some database. Right, we can do the keyword match. But then I hope you can understand that the query that the user asks, and whatever form the information is present in the documents may not be using the same keywords, right? The keywords may be different. For example, let's say the query is about what is the policy on time off, right? Now, what is time off? Time off is, vacation period, right? So let's say your database contains words like vacation, and the user asks about time off. Now, there has to be some way to ascertain that this time off actually means vacation, right? So you can understand that a keyword search is not helpful, because you will not be able to look up the right data from the database. That is why we use embedding model, which converts the chunks into contextual vectors which contain the meaning of each chunk, rather than just a keyword search. We can search for vectors which are semantically similar to the query asked by the user, right? So all these vectors, which is all the chunks convert into vectors or embeddings, will be stored in the vector database. Okay. And whenever the user asks a query, this is user's query, that query will also go through the same embedding model, and that model will produce an embedding. Okay. Then what we do is we search for the closest embeddings in this vector database, closest to the user's query. Okay, for example, if somebody asks this best coffee shops near me, and then there is a vector in the vector database which is about top rated cafes around your location. So you can see that there is no exact keyword match, but you know that they are similar. So in the vector database, they will be close by. Let's say this is user's query. This is user's query, and these are some vectors present in the vector database. So you can see that there are some vectors which are close by. Those are the vectors which will be containing the information which is closest to what the user asked. So that is an advantage of using embeddings. Okay, let's now go over fine tuning. This is something that you have done already, right? What is the difference between RAG and fine tuning? Let's go over this so that you know that given a scenario, what is it that you should go for? Should you go for RAG or should you go for fine tuning? So this is something that you should be clear with. Okay. So you would have understood by now that RAG adds external knowledge to the model at query time. At query time, which means the moment user asks a query, we fetch the required vectors from the vector database, and we kind of impart that extra knowledge to the LLM. Okay. On the other hand, in fine tuning, as you know, fine tuning changes the model weights. In RAG, we are not in any way touching the model's weights, right? In fine tuning, we change the model weights so that it learns from the new data that we feed to it, right? So that is one big difference. The other difference is about the kind of data that is needed. As you have seen already, in RAG, you can pass in any kind of unstructured documents like PDFs, notes, web pages, JSON documents, CSV documents, CSV files. All these kinds of data can be passed to RAG, right? However, if you want to go with fine tuning, you know that you have to convert the data into a nice format, right? In supervised fine tuning, it has to be converted into features and label. So this pre-processing you have to do, and those that data should be having task specific examples, right? So that's another big difference that you should keep in mind. So what kind of data you have, you should based on that data you should consider whether RAG is suitable or fine tuning is suitable. The next difference comes in the scenario, the use case into which you want to apply any of these two scenarios. So as I told you, RAG should be used in a scenario where the knowledge keeps changing, right? So if something that keeps changing, you can't keep retraining, so RAG is a better option. Whereas fine tuning should be used when you want to kind of teach a new skill to the model, right? In some sense, you want to teach some new skill to the LLM that is to stay, that is not expected to change, right? In that scenario, you will use fine tuning. And finally, the cost wise, fine tuning is expensive. It requires powerful GPUs because you have to train, you have to tune so many parameters. Okay. RAG, on the other hand, is much cheaper. What is the cost involved in RAG? The cost is involved in embedding, preparing the vector database, and during the runtime for accessing, right? So that's not as expensive as retraining the model, okay? And the moment your data changes, simply change the data source of your vector database, which means just create the embeddings again of the new data and update your vector database. So that way, again, it's very efficient. Yeah, so this is what I just now spoke about. It's very easy to bring in any change in the data associated with RAG. On the other hand, in fine tuning, you have to retrain the model, and that requires a lot of time as well as cost, right? So these are some examples. Let's say there's a chatbot which has to answer some policy questions for a company or an organization. So policies might change probably soon. So this chatbot can be given all these documents which contain different pieces of information about the company in the form of vector database. So RAG is suitable there. On the other hand, if you want to change the way model behaves in some sense, right, then you should prefer fine tuning. Okay. All right. So how do we implement RAG? Let's talk about that. There are several frameworks. So as you saw, there are several steps that are involved in RAG. So we need some kind of framework which kind of combines all these steps. There are several that we can use. LangChain is the most popular. It provides a lot of functions to perform all these steps. And then Llama Index is there, which facilitates easier indexing. And then Haystack is there, which is also very popular for NLP operations. So in the demonstration, we are going to use LangChain, the first one. Okay. Finally, to sum up, what we saw is why RAG is needed, which are the situations where RAG may be applicable, what are different steps required to implement RAG. And the big picture that we understood is when we want the model to not make up facts, not hallucinate, then we would want to make use of RAG so that it looks up the required information rather than just making up stuff. Okay. So that was kind of a broad overview to RAG. So next we'll see how to implement RAG in LangChain. Thanks.